Just like with almost everything, you can memorize your way out, or you can try and apply it out. We'll talk through the application-ish, but even that gets a little bit of a struggle with this particular reagent. What do we see as the reactivity?
The alkene.
Okay. We've got the alkene. I'm going to change that up. And in particular, when you say the alkene, what are you actually saying is reactive? Okay, we've got the pi bond as reactivity. All right, is that it? There's roar. Okay, just in your phrasing of that, I think you've memorized it.
Definitely.
Okay, so let's avoid that. If we look at roar, R as being any kind of R group, typically when we're considering this molecule, if you're going to look at it on a test, you're probably seeing something along these lines. Not a big deal with this information. Roar, you'll see it as roar or you'll see it drawn out like this, but ultimately it's still hinging on the exact same chemistry. The weakest bond in that system is the OO bond. Okay? So we've got our alkene pi bond and that OO bond. Which bond do we think is the weakest?
But equally is weak.
Okay, why do you want to say equally as weak? It's fine.
Because it's an oxygen connected to an oxygen, it's a carbon connected to a carbon.
Okay, so they're both nonpolar covalent bonds because we're by definition looking at the exact same electronegativity between those. Okay, except when we look at that carbon-carbon bond, those electrons are being shared fairly well, relatively low electronegativity. What's the issue with oxygen?
High electronegativity.
Very high electronegativity, which means while they are technically sharing electrons, more or less the distance between those is going to be a little bit more spaced. Okay, and if we start to open that up, what does that mean?
It's more likely to break the bond.
It's more likely to break. How should that bond break? So if we're now going to say the roar bond is our more likely one to break, how should it break apart?
Into two radicals.
Why should it break into radicals?
Because I know roar makes radicals.
Okay, which is fair. Okay, this would be that memorization part. If you see roar, you should be seeing radicals. Okay, why should it break into radicals? Is there a difference in electronegativity to cause it to polarize one way versus the other? No. Okay, so that bond should split into radicals.
But that doesn't always become a radical, does it?
Roar does.
When it comes to roar, it does?
Yeah.
Okay, gotcha. Because when we were talking about BR2 the other day, we thought it would become a radical, but it just didn't want to the electrons the other.
BR2 does become a radical.
It does?
Yes.
What do you mean?
BR2 becomes a radical under slightly different conditions. It's slightly lower in electronegativity, so it's a harder bond to break. Roar busts with thermal energy. Okay? Bromine busts with UV radiation. So if you were going to expect the bromine to break apart into radicals, what you would also see is H nu. That H nu is what's causing this to break. You usually see a wavy line, and then you see the H curve EV symbolizing light. That light energy is higher in energy than the thermal energy necessary to break apart the roar. So BR2 absolutely does split into radicals, but that requires a light excitation to cause that to break. Typically when we see bromine, we're not talking about it in the presence of light, so why would it split? It doesn't split. What causes it to split? Being near an electron source. If it is near that electron source, that's what causes the bond to polarize, and that's what causes that to break. So BR2 in and of itself isn't just splitting and forming Br plus and Br minus. It is being forced into that scenario by having a nucleophile come in and react with it. Okay? So we now have a radical. Roar radical. Technically not a roar radical. Technically it's just rho radical. Rho. Right? Because there's two of them. Welcome to Scooby-Doo. So now what does it react with? So now we could introduce the pi bond. I'm going to flip it so the pi bond's a little bit closer. Radical comes out, radical comes out, radical goes in. And we form RO bond now to our carbon structure. And that carbon structure still has a radical. We would predict it to form in this fashion as opposed to the other way, because this way gets us a tertiary radical as opposed to a primary radical if we broke it the other direction. Does that make sense? Okay, enough head shakes, yes, I won't draw it. Okay, is this a final product? No. How do we know it's not a final product? It still has a radical. What's that? Okay, so now we encounter an issue. What does this radical most likely encounter? Okay, there was a suggestion that we still had another row floating around. How much row have we formed? This is just a silly conversation to have, but we're doing it.
2 times the amount there is of roar.
Very, very tiny amounts. Okay, even breaking that bond, you're looking at insanely small amounts. Roar is always added as a catalyst, not as an active reagent. Is that clearly stated within this question step? No. Will it ever be? Probably not. It might be, but probably not. Okay, which means the presence of rho, the rho radical, next to none. So the odds that we get this carbon radical to encounter that rho radical is non-existent. So what does it encounter? More pi bonds. So it reacts. And yes, what you're mumbling over there so that nobody else can hear you, okay, useful. We're going to spin that a little bit. Is we get another radical. Well, now what does that see? Another pi bond, and another pi bond, and another pi bond. Okay? This will repeat until by random chance we do happen to have a radical meet up. Very slim possibilities of that happening, but eventually it does come true and it does happen. So the end result, okay, is we would run this cycle multiple times over. There's our double arrow saying it just goes. Okay, and if you're drawing all this, you probably don't want to. That's okay. You don't have to. Don't blame you. Okay, so on and so on and so on. Okay, so what is our result? Okay, is it an addition product? Did it do an addition?
Not necessarily. Isn't radical chemistry its own subset?
So is it addition? Yeah, it is technically an addition reaction. Okay, because we did lose the pi bond and we formed 2 sigma. But then we lost another pi bond and formed 2 more sigma. And then we lost another pi bond and formed 2 more sigma. So while it is an addition, it seems like it's still going. So what we might do is look at our other answer choices. A repeating chain. We look at our final answer, does that match? Yeah. Do we form a cyclic alkene? No. An ether? Okay. You might again say, well, don't I have an ether right at the beginning? Yeah, but what's the majority of the structure? Not ether. Okay. You remember, well, that's kind of challenging. How do I figure out? There's 3 answers that match. It does say best. Which of those 3 answers best represents the final product? A repeating chain. What is a repeating chain oftentimes known as? And this is a polymer. We're talking about polymer chemistry here. Okay. It is something we will talk about again later on in the semester, but this is kind of the first-ish case where we talk about polymers. This is a radical polymerization, okay, in this particular fashion. And what we're talking about is reacting out our alkenes to generate this product.
Is there non-radical polymerization?
Yes. Okay. You heard about DNA?
Oh.
Guess what DNA is? A polymer. It's a biopolymer. Why do we add the word bio in front of it?
It's biological.
Because a biological system made it, so we call it a biopolymer. Okay. What are muscles made out of? Really? Nobody knows what muscles are made out of. Made out of proteins?
Oh, that's what you...
And what makes up proteins? Amino acids as individual units that you then link in a repeating chain. Muscles are biopolymers. Okay? Same principle. Okay? So when you go through and study biochemistry, you'll start to look at those polymerization reactions and how do they work. If you've already studied some biology, you might have heard of some of the names like DNA polymerase, polymerase. It's the how do you make the polymer of DNA? That's literally the name. Okay, they just add the ace at the end because they feel like being special. There's, I think, a Latin root for it, but whatever. Okay, that explains that. So most of your enzymes will carry that ace ending as a signifier that it's an enzyme that's going through and making that. Okay, so this is the first case where we see it with our radical polymerization. We'll talk about sort of the biopolymers, a little bit more based in the lab than in the lecture, but we'll do a polymerization lab where we do both the radical polymerization and we're just going to use the term condensation polymerization, which is a non-radical polymerization in the lab, and we'll just kind of play around with that just to see how it works. Make some pictures, that kind of fun stuff. Okay. Does that help answer that question? We good, Ivan? Yeah. So what we worked through here was trying to figure out kind of the chemistry behind it. A couple people both chimed in right away knowing what was going on with ROR, and ROR is a red flag for radical. Okay. Once you know it's a red flag for radical, you're going to start to form radicals, and now the question becomes, what could it react with? Typically, when we talk about ROR and alkenes, we're almost always adding a special reagent like HBr so that we can do a radical addition of HBr. If we get rid of HBr, that now changes the chemistry and we get this polymerization process. With the presence of HBr, that cancels the polymerization and we just get the addition. Right? And that has a lot to do with the overall chemistry of those individual molecules being involved in it. Kind of, sort of? Okay. Questions? What's next? Okay. We're going to switch this up. Compare the reactivity of, what do I want to do? Let's pause the video.
Based on how well it was able to hold that negative charge.
Okay. If we're going to rank according to base strength, what was a base?
Negative. It has electrons rotate.
Electron donor.
Okay.
Yeah.
An electron donor, in particular an electron donor, 2 H pluses. Okay, but if we're looking at ranking base strength, they're always going to be H pluses, so that's not going to be a relevant thing to talk about. We need to look at instead of the electron donating ability. If we're talking about the electron donating ability, what should we be looking for as signifiers for that?
Electrons? Lone pairs?
Lone pairs, electrons. Okay, that's fair game. When you look at all three of those, what are you seeing? Is it just the electrons?
And the charge.
It's not just the electrons, because there's electrons up here, and I don't think anybody talks about those. Where did you start? You didn't. You talked about the pi electrons, which is a whole different system.
Electron is
Okay.
electron is electron.
Unfortunately not.
No.
Okay? You start with charge. So when we're thinking through that reactivity and trying to come up with it, that's why we have a ranking system. That's why we have quote unquote Cario. I just realized you got it flopped. Okay? But that's why having that written out as a reference can help you out. Okay? That's why you want to be going back to that. Because it can help you focus your thoughts on how you move through it. Okay? So we would start with charge.
They're all negative.
They're all negative. So do we have a difference?
Nope.
No. So now what do we move to?
Size.
Size. Do we have a size differential?
Yes.
Technically, but they're all.
God, now we've run into an interesting dilemma here. Is there a size differential? Are those molecules different sizes?
Yes.
Yes. Do we care?
No.
No. Because when we talk about size, what are we talking about?
Atomic size.
Atomic size. The atom that holds the charge. Why do I look at the atom that holds the charge and not the other atoms?
It's the most reactive.
That's the reactive site. So we're looking at carbon, oxygen, and carbon. Are those carbons obvious? You can sit down if you want. You can stand too, that's fine. Are those carbons obvious to you?
Yes.
Okay, some people say, whoa, that was exciting. Okay? Some people say yes, by all means, that's fine. You don't have to specify them. If you're like, well, I don't really see a carbon there, then that's fine. Be explicit. Make sure that you can see the motherfucking carbon, right? Explicit. Okay? So now you can start to have that. So now we can say, well, size. Is there a size difference between carbon, oxygen, and carbon?
Yes.
No, I mean,
Between
there
oxygen
is,
and carbon,
but
there is.
And here's where we encounter one of those dilemmas that shouldn't be a dilemma for you because you had OChem 1 with me. And the very first lecture of OChem 1, and multiple times throughout the semester, we talk about the size difference on our periodic table. Carbon and oxygen are located in the exact same row.
so they're basically the same size.
They are effectively the same size. That size differential is irrelevant to the overall chemistry, which means bullet 2 isn't useful to us. Right? And why is it better to reference the size being irrelevant than actually pointing out the size? 9 times out of 10, you ask somebody to rank the size difference between carbon and oxygen, and guess what you're going to get? The wrong answer. Which one's bigger? 9 times out of 10, there it is. Okay? Carbon is bigger.
Because it doesn't hold.
Oxygen has more electrons. You're right, but it's putting them at the exact same energy level. So not further from the nucleus, but the nucleus is stronger because it has more protons, thus drawing the electrons in tighter.
Oh, sure.
Damn! That's why it's easier to just say across the row it doesn't change. Because again, 9 times out of 10, you get it wrong. So don't look at that size difference because it's negligible in the grand scheme of things. Okay? So size is irrelevant. What do we move to next?
Electronegativity.
Electronegativity. So we use our chi because we don't like writing the word. Okay? The difference we're looking at is carbon versus oxygen. Is there a difference in electronegativity? Oxygen is more electronegative. So what does that mean?
There is a difference.
There is a difference. What does that difference mean?
Different reactivity.
What is it doing with its electrons?
Hold them tight.
It's holding them tighter. What does the base need to do?
Donate some
Donate.
electrons.
Right? So if oxygen is more electronegative,
It's
not
gonna be
going to
less
take
likely.
it's less likely to share those electrons. So we could go through and say our least, and we could put oxygen down there at the bottom based off of electronegativity. We still haven't defined the carbons, so what can we do? Compare A and C according to electronegativity.
B and C.
Okay, we can compare B and C. according to electronegativity, we're still going to get B being least. So we know B is the least, we don't know where A and C are. So we need to figure out where A and C are. So what do we do?
Compare them to B.
Move to the next thing in our line. Now we can look at resonance. Is there a resonance effect here?
Yes.
Okay. What is that resonance effect telling you?
That it's going to be more stable, whichever one has resonance.
On A, the electron pair
Right.
will.
And again, we have to be careful with saying resonance necessarily means more stability. Not necessarily. I'll show you a direct conflict to that in a second.
Oh no.
So the pi bond on the oxygen it'll move the electrons onto the oxygen, so that way the.
Okay, for the sake of the recording, take the pi bond on the oxygen, so we're only talking about A, because it's the only one with pi bond. Take the pi bond and move it up to the oxygen. I would argue no. You're not inherently
The
wrong.
electrons in the pi bond.
No.
No, dang it.
The pi bond was the wrong place to start.
Maybe the charge, the electrons in the charge.
Why should we start with the charge?
That's where the active.
That was our primary reactivity. So focus where you have the chemistry first. Well, that's an eraser. You didn't see much, but if you look real carefully, 20 minutes and 20 seconds, 21 minutes and 20 seconds, you'll see the carbon start to fade. Okay. The electrons from that carbon can go up to forming a new pi bond, which exceeds the octet on the carbon, which then
Moves the electrons onto the oxygen. The charge is there instead.
so we'd get a new drawing. The relationship between those structures now being resonance with our double-headed arrow. So if we're now going to compare A to C, what do we say?
So there's more resonance in A than C.
There's more resonance in A than C. What was the question?
Which one's more reactive?
What was the reactivity we decided to define?
Strength of a base.
Base. So,
C would be a stronger base.
C could be a stronger base than A. Come on, Ben, work with me. Okay.
That's not right. Is it? Don't we have to compare A and B?
Okay. Did we already compare A and B?
Not really.
What was the charge on A? Negative where?
Carbon
Carbon versus B
on an oxygen.
on oxygen. Where's the difference? Electronegativity, which would suggest
Is less reactive.
B is less reactive. Right? So did we already compare it? Yeah.
Yes.
Let's lean into your push here a little bit. You have a resonance structure, right? Which of those two resonance structures should you be evaluating? We're talking about reactivity. Top or bottom?
Both at the same time. They're both true at the exact same time.
Okay, true, but if we're going to talk about, I always have bad examples, but if we were talking about a fight, we could talk about where someone's hands could potentially be. Do you care that someone's hands are over here? Presumably you're fighting with me in front of me. Do you care that my hands are over here? No. Do you care that they're over here?
Yes.
Yeah. Right? The hybrid, which is exactly what you're talking about, is the mix. It's where my hand can be at any of those points. It's only relevant when it's directly in front of me. So which of those two structures is the most relevant one to look at? Which one is the most stable?
The top one,
Why is the top one more stable than the bottom?
because the oxygen is least likely to donate its electrons.
There's other two.
Oxygen, being more electronegative, would rather hold the electrons. This introduces an interesting dilemma for us. We were originally drawn with the negative carbon, and yet what we're saying is the negative oxygen is the more stable form. And if we compare the more stable oxygen of A to B, Now what do we have as a dilemma?
Well, now we have to go down the list, right?
Because we'd be oxygen to oxygen. That's not going to be electronegativity anymore.
It's going to be resonance.
It's going to be resonance. Everybody see that? So depending on the structure that was given to you, you may have been given a quote-unquote bad structure. It's not technically bad. We'll address that in a second. Okay? You have to be able to recognize those other intermediate resonance systems to be able to come up with a fair ranking between them. Right? So if we're now comparing A to B, charge, size, electronegativity, all atom effects are all the same. We would then move to resonance. Which one of those has resonance?
A.
Which means?
C is more stable.
Ooh. These two should swap. Right? That's interesting. Because of where we started, that was a negative carbon compared to a negative oxygen.
The oxygen is more stable.
Right? Trying to track that difference can be very, very challenging to nuance. Okay? It turns out that that difference is really relatively insignificant. Right? And if we look at the conjugate acids for each of these two compounds, they have almost identical pKa's, which is interesting. If you look at the conjugate acid for that carbon structure that we started with, that would be acetone. Acetone has about the same acidity as water. That's wicked. You're removing a hydrogen from a carbon versus an oxygen. And it's okay to remove that carbon from that hydrogen because of that resonance stabilization. That becomes a secondary feature within our drawing. Everybody kind of see that? For the sake of this question, what I would be looking for is the explanations behind all of these. Okay? And I'd want to see that clear explanation. If we look at what I've got up here, I've got a lot of structures, right? Do you see all of those structures up on the boards? More or less. I mean, this one at least drew the resonance. Did you draw resonance over here? No. That's going to be hard for me to be able to interpret and give you credit for it. Okay? The explanations that I'm using, I've identified charge, size, electronegativity, resonance. I'm putting out the orders behind those so that I can see that. This board has called that out. They're acknowledging that those pieces are there. You have the answers over here, but you don't have the ordering behind that logical flow. That can make it harder for me to assign points. So what you're trying to show is the maximum amount of knowledge possible within a tiny little amount of time. So get down what you can as quickly as possible, move on. If you get more time, come back, add more. Does that make sense? How much time should you spend on this question?
2 minutes. 1 minute.
Minute and a half. It's about all you get. Right? Because that's about all you get on the final exam. So it's the same kind of process. You still only get a minute and a half to put that information down and move through it. And again, every semester, oh, I can't write it down. I need more time to be able to write it down. The best scores that I've ever seen were coded all the way through, multiple choice and short answer, coded with pencil lead, because they wrote something for every single question. Those were the ones that scored the highest. And it's not because they ran out of time, it's because they wrote stuff down. It's that writing it down that gets it out of your brain where your brain can jumble stuff up. Right? And where you're actually wasting time is looking at it being like, I don't think I need to write something down. Oh, no, maybe I do need to write something down. You just wasted time trying to not write it down. Commit out of the gate to writing it down. Right? And that is challenging, but that's the best approach. Some caveats, just for the record for everybody, because Alex is potentially new and the rest of you probably don't even remember. What's the first question you start with? What's the first question you start with? So I heard multiple choice, writing your name down. Let's go with writing your name down. Right? Are you going to forget your name by the end of the exam? No. Are you going to forget Cario? Maybe. We've been working on that Cario process a lot, so maybe you won't forget that. But how a Diels-Alder reaction works, are you going to forget that? Yeah, probably. Right? So maybe what you should do is not start with your name and instead focus on the exam. But now where in the exam should you start? Short answer or multiple choice? You get people going back and forth on that. You go, well, short answer is worth more points, so I need to do those. Multiple choice can be faster though, so I should start with those. And to both those explanations, I say you're wrong.
Questions you know?
Start with a question you know. That's going to be different for every single student. And that takes time to find. So you need to be scanning through the exam, and if you see a question that like jumps out of the page, 3-dimensional like a fish, and slaps you in the face, that question you should start with. Get the answer down on that one, right? Because that's one you know, done, you move on. You've guaranteed points, right? One of the problems with this method is if you go through and you're like, oh, I don't know anything, you can start to spiral, right? And I fully understand and get that. But what you're trying to do is work through the ones that you know the most about first. You will always find questions that you don't know. Right? I don't think a single student, in my experience, for any exam I've ever even been a part of, has perfected a test in organic chemistry. And I'm talking about tests not written by me as well. Right? It just doesn't happen. There's too much stuff to process. Right? So don't worry about being perfect. You can try to be perfect, but try to be perfect by proving what you know. That's the point of a test. Okay? On your end. On my end, the point of the test is to find out what you don't know. So I've got to ask a whole smattering of questions across the board to figure out where you're broken. Right? That's test philosophy that people sometimes disagree with. They go, oh, that's not fair. Dude, if I take my car to the mechanic to get it fixed and they kick the tires and they're like, oh yeah, there's air in the tires, this is good to go, and then the engine falls out a mile down the road, I'm going to be pissed. Because when I take it to them, it's to find what's wrong with it, not prove to me that there's air in the tires. Right? So the test is going to push you. Focus on what you know. Get that as much down as you can, and as best as you can, ignore the rest. Okay? 2 other things that are going to happen when you take a test this way. Okay? Potentially 2 other things. Number 1, when you finish the test, you will feel like utter crap. Because you will have spent the first 15 minutes dumping all the stuff you knew. It's a 75-minute frickin' exam. So that means you will spend 60 minutes of the exam focusing on all the stuff you don't know. That's going to feel miserable. Okay, so you will feel awful finishing the exam. But you will tend to forget the parts that you did well on in the beginning of the exam. Which means the other thing that comes out of this is that your exam score on net is higher than if you just went through and started with multiple choice or started with show your work. Because you started with the things that get you points. That's the point. That's how you should tackle a test. Okay? Last little spiel. This was a mind thing for me. Like I always took tests, first question through. When I switched, it was a big difference. And the thing that helped me switch was for the first 5 minutes of the test, I refused to write anything down. Because what's happening in the first 5 minutes of the test? It's less of an issue in this size of a classroom. Everybody's grabbing the exam. Everybody's amped to high hell. Right? Your blood pressure's through the roof. You're flipping through the exam. Right? There's noise, there's distractions, and you're losing your shit. Right? Why are you writing stuff down in those 5 minutes?
So you can remember.
Right? If it's things that you need to remember, then in the first 5 minutes, start on that first page, don't look at the rest of the exam, and just write down the stuff that you wanted to memorize. That's done. Focus on purging, not starting. Then after your 5 minutes are up, then you can calmly turn the pages, read, scan through, find your questions, and then start the process of, oh my God, this is awful. Okay? Kind of, sort of? What's the next question?
Multiple choice.
Oh, Lord. You've already heard me starting to grunt and groan. Lesson learned. More reps but less weight is a lot harder than less reps and more weight. This was supposed to be like a dead week. It wasn't supposed to be like dead body week. Okay, so how many non-identical products are here? This is a challenging question, okay? If you've read through the textbook goes through and explains this in nice, gory detail behind everything. So we'll sort of pass through some of it. What's the most reactive thing here? Okay, pi bonds. No. It's reactive, but again, no.
The reactant.
What about the reactant? The deuterium. Well, dude, how the heck does deuterium react? Yeah, that's why it says up there, D is deuterium. It's heavier, so not quite the same as hydrogen, okay? But that heavier doesn't really change the chemistry as far as we're concerned, okay? So when we see DBr, it's the same thing as HBr, except I can put a D instead, okay? Why would that matter? Well, let's push on this a little bit and see what happens. So when we go through and look at the reactivity, hopefully we see that our D is positive, and then we have the bromine or bromide, technically as our negative, okay? That D being positive is our most reactive thing, and we need to stabilize that positive with electrons. Where were those electrons? In the pi bond. Okay? Is there a difference between either end of those carbons? We call this purple and we call this one black. No, which means where could the D go? To either of those spots. So I could put the D here. Stupid. Or I could put it here. So fucking stupid. Okay, what reacted?
The deuterium.
Deuterium with what?
Electrons?
Electrons found where?
Pi bond?
Where are they in the pi bond?
And the bond.
In the pi
Above and
orbitals.
below.
Above and below, which means
Dash.
I could have this deuterium be wedged, or at that exact same site, I could have that deuterium be dashed. Just like with the other position, I could have it be wedged, or I could have it be dashed. Does anybody want to complain about this?
They're all the same.
Okay? They would all look the same, but there's something missing in our potential products. What's that thing missing in our potential products? Before we even get to bromine, you're right.
Hydrogen. Oh, the other charge.
Carbocation. That carbocation should add a little bit of asymmetry to these to make these, we're not quite officially there fully, but should make these not all identical. Now what would happen?
Bromine would come.
the bromide would come in. Okay? And so the bromide could react with that positive. Ew. Stupid computer. And I could put the bromide here. Oops. The bromide here. Where is it? Bromide and bromide. Right? Why does that spot also have stereochemistry?
Because it's also coming in above or below 210.
That bromide is still also coming in from above or below, okay? Which means that could be wedged. Or that could be dashed. The other one could be wedged. Or dashed. Getting the idea? Okay. So I need to draw out a whole bunch more products. As I'm drawing it out, perhaps Caden will chime in now because you were the one that noticed the other issue. What do you want to chime in with?
Well, there's still some that are the same, so they're just repeated,
Some are repeats. So what are you now responsible for trying to figure out?
which ones are the same?
Yup.
That's about one.
I think I've got them all. So now it would be a question of trying to figure out which ones are copies, which ones are not, and trying to parse it together. Okay? All of that's going to involve some kind of three-dimensional manipulation. If I take this structure right in the middle and I flip it over, the bromine would become dashed, and the deuterium would be wedged. Wedge dashed. I like the middle structure better than the one on the outside. Okay, so I'd get rid of that one. What other ones do you see?
Isn't the top right the same thing, no?
Both wedged would be the same as both dashed.
Top right, if you flip that over, the deuterium would be dashed and the bromine would be wedged. Okay, so that's not going to be the same as this because the deuterium would be at the top versus the bottom, but it will be same as that one.
Top left and middle right on this side.
Top left, middle right, agreed.
The bottom one and the middle, so
Yeah, I was about to cross out too. Yeah, so that one is the same as the top middle.
these are supposed to be.
Okay, so are we then there? Yeah. So now it's 4. Does that suck? Yeah. Okay. On an exam, where would I place this one? This is probably middle of the pack. I probably wouldn't do this one first. I might start it and then be like, oh God, stereochemistry. Okay. But I'd have that work started so I knew what I needed to do, and then I would move on. Okay. And then hope I could double back to it. Okay. If I can't double back to it, I could go through and be like, there's tons of stereochemistry involved in this, so what's my most likely answer? 4, because it's the most as possible answer choices. Okay? That's a very half-assed approach, but if that's what you got, that's what you got.
I mean, it's gonna be a multiple of 2, so you only cross out 2 answers from that.
Okay? Kind of makes sense? What are the relationships between these products? Which is a whole nother level to add to it, but that's still a fair game kind of question. So how would we define all of those relationships?
So there's 2 pairs of enantiomers, and then also 2 pairs of disastomers, or how do you say that? I still haven't learned how to say it after a full, almost a year of this stuff.
Blame me, that's fine. It's just fair, like half the time I say it wrong anyway. Okay, so those ones should be enantiomers. If we take these one and we take that and flip this one over, we should see it's the mirror image there. So these are enantiomers. And then hopefully what we see is these are our disastomers. See? Even I was saying it wrong. And then these two. Diastereomer.
Yeah.
Right. So we get 4 products with all those individual things. Why use the deuterium instead of hydrogen? Well, if we use hydrogen, would that be a chiral spot where our deuterium is? No, so that drastically simplifies the amount of products, and that cuts this all out. And now it's what's the relationship between all those products?
They're all the same.
Now they're all the same. Okay? There is no chiral center in there. So we add that deuterium there to really test, do you understand the mechanism behind this? So that's where you'll see these weird atoms kind of appear, because what we're asking about is, do you understand the mechanism? Okay? Without having to draw a whole bunch of lipid mechanisms. Make sense?
Just out of curiosity, would there be one that's out of the 4 that out of the ones that were the same? Different, non-identical products. Would any of them be the main product or the more likely product of this reaction?
So that's an interesting question, because when we get multiple products, okay, and we've talked about this, right? When we got 2 products, we could reference some of potentially them as kinetic versus thermodynamic. As you run this reaction, is there any kinetic versus thermodynamic imbalance? Well, in that very first step, the pi bond is reacting with the deuterium. Is there a difference between the top and the bottom of that pi bond? No, it's perfectly symmetric. There is no difference. So we would expect both the top product and the down product. Okay? Oh, I just crossed out things weirdly. What about for the next step, when the bromide comes in? What is the bromide reacting with?
The carbocation.
The carbocation. Is there any difference between the top and bottom of the carbocation? You have deuterium on there instead of hydrogen. Could that make a difference? Yeah. Yeah, it could. Okay. What is that? I don't know. Okay. But would that deuterium potentially have an effect on this? Absolutely. You're changing the dynamics of that, which could change how the bromide potentially interacts. Okay. Maybe that deuterium is ever so slightly larger. I'm not convinced it is. But if it's larger, then the bromide's going to probably preference the bottom versus the top. So you might see them more as a trans potential product as opposed to a cis.
Because I guess if the deuterium is larger, and then how big bromine is, it's going to have a harder time.
Right. Generally speaking, deuterium versus hydrogen has a negligible effect to at least our approximation for the sake of this class. So if you're seeing deuterium present, we aren't trying to do something goofy or strange or trick you. What we're really just trying to do is make that a chiral atom when the deuterium's added, so that we can have a discussion about effectively the mechanism. We aren't saying, well, what is the isotope effect on how this reaction works? Okay? Will you encounter that? Are you a chem major? Then yeah, you might. You might encounter that in a physical chemistry class. Everybody else probably doesn't have to take physical chemistry and don't need to worry about it. Okay? But it is a subtle effect, but it is a visible effect when you're looking at it with the proper equipment. Okay? We have a hard enough time, and by me have a hard enough time counting to 10. We're not going to worry about what instrument we need to detect the difference between a 1 and a 2 mass. Okay? Make sense? Next question.
Number 16.
Oh yeah, back to nomenclature. Yay. So I already heard some people sigh, so it sounds like I have already poisoned you. Good job, Mike. And apparently I like multiple L's. This is one, again, I would straight up skip. At the end of the test, maybe I would try and come back to it. This is one that you would probably aggressively see me mumbling to myself on the same side, trying to make sure I get that Z with the double bond correct. Okay, so on the same side, I need to make sure I'm getting my groups on the same side. So I would go through and start with that. That's opposite, so A's wrong. B's got them on the same side. C's got them on the same. D's got them on opposite sides, so that's wrong. Okay, so I would have narrowed it down to B and C. Where would I go after that? Well, actually, everybody understand why I went to Z or E, that analysis first? Okay, that's still planar. That's not three-dimensional. That's just where those groups are relative to the double bond. So as an approach for me, that's pretty lightning fast solving-wise. Okay? You may see things otherwise, and I see exactly what you're doing. Okay? Admittedly, I would probably not deal with the RNS first, hoping that I could get out of the question without doing it. Okay? A real quick look at my answer choices, though, I'm not even going to bother to skip it because that's what the question is going to ask. Okay? So the pent and the all, irrelevant, because the only difference between these two structures is the wedge versus the dash. So I have to do RNS. Okay? Which of those two structures would I start with? Okay, which is a little bit weird. I'm going to start with C. Not necessarily because of the wedge. You're right. But my emphasis is not the wedge, it's the implied hydrogen that is dashed. That implied hydrogen will, by definition, be the lowest priority when I go through to assign priorities, and so that would hit me at a 4, which means I just have to figure out which way I turn, and now we can go back to our hand gestures and signaling the devil. Right? So now, how do I assign priorities for the rest of them?
Weight, size.
Atomic mass is what it comes down to. Okay? So I'm looking at oxygen versus carbon versus carbon. Oxygen has a higher mass, so it's my number 1. So now I've got to decide between those other two carbons. Well, they're both carbon, so I don't have a difference at the atom, so I have to go further away. When I go further out to the carbon on the left, I go out to the highest priority thing. On the left is the other direction. And I would go out to a carbon. If I look at the carbon on the right, what do I go out to?
Hydrogen.
A hydrogen. Do I have a difference?
Yeah.
Hydrogen versus carbon. Which one has the higher atomic mass? Carbon, which means
The left one is
2, 3. 1, 2, 3. I provided feedback on this question. I did this exact same stupid thing. I did 1, 2, 3, 1, 2, 3, 1, 2, 3. Like saying 1, 2, 3 again was helping me. But what I'm doing with my hand is constantly spinning that circle and saying, which direction am I turning? And for me, whatever reason, doing it 1,000 times helps me to increase the odds of not fucking it up.
Turning counterclockwise.
Okay? And I'm going counterclockwise. And if I go counterclockwise, that would say the assignment on that carbon
I'm just excited to hear the answer to you.
is S.
Okay.
It's because you were hoping I didn't screw it up? Yeah. Thanks. Okay? So I would now say that is S. I go back to my question. It says R. That means C is wrong. Because I eliminated A and D, I'm done. I'm not going to bother to check what's going on with that. My answer, circling that, is a bad idea. You should cross that out and then circle this. I'm going to say my answer is B.
I was excited to hear the answer because I couldn't tell which one it was. I was
Okay.
such an RNS.
Yeah.
Well, just imagine I'm driving and whenever I turn the wheel, this car will turn.
So, and I'm not going to. So, but when you turn it that way, you're turning it to the S?
Sinistra is like.
Yes, because you know a different language.
I just think of right.
Yeah, you could think of right, and that works for the right. There are a variety of methods. They're all inconsistent for me, is ultimately what it comes down to. Okay, so whatever consistently works for you, use it. Every time I do these, I have to go very painstakingly, slowly through them and make sure, or try to make sure I don't screw it up. Okay, these are probably my lowest success, like percent success kind of questions, and I'm after whatever it is, 20 years of doing OChem, I'm probably like 85% confident in my answers. But every time I'm like, oh God, okay, I think this is the answer. And then whenever I check, it's like, did I get, I think this is one of those 85 times. Okay? And it just comes with practice and being able to manipulate those rules. If you know that, you're fine. If you don't, sorry. Unfortunately, you picked me as your teacher who sucks at this. Okay? I will say I've tried to use shortcuts that have been found online, and the shortcuts have always proven inconsistent for me, which could just be me, like being an idiot using that shortcut. But there have been a couple shortcuts that I've seen that I've been like, yeah, that will work 50% of the time. And people are like, oh, that's okay. I'm like, motherfucker, don't do that process. Just flip a coin. You'll get the exact same result. Right? Because it does boil down to just a 50-50. So if you're not better than 50-50 with whatever method you're using, you should just flip a coin. Okay? Next question? Better not be another one of these. Okay. Just check. Oh, Deal's older. I think Deal's older. Yeah, Deal's older. This is one, admittedly, I was in tutoring trying to write explanations for this, and this is one that was really challenging for me to do because I was being insanely stubborn. And by insanely stubborn, what do you think I was refusing to do?
Build a model.
Building a model is up there, but I was definitely going to refuse to do that, and I would recommend you refuse to do that on the exam too. That's a lot of time investment.
Draw it out.
Draw it out. I tried to do it all in my head. I think I got it. But yeah. So this is where, hey, you got those color-coded pens for a reason, man. Pull them out. Use them on the exam. Yeah, everybody watching this video that's not in this class be like, dude, he gave out color-coded pens? Yeah, because, such a jerk everywhere else. I got to make up for it somehow. Have a pen.
Ooh, pen.
It's like the pizza party at the end. Okay? So if we're going to make this connection, for me personally, I find it easier to see that kind of connecting kind of underneath. So those dashes I'm not really showing as dashes, or not intending to show as dashes. I'm trying to explain this for how I would write this out. Okay, so those are still solids, at least in my head. When I do this attack, I'm bringing that in underneath. Because I'm bringing it in underneath, come on over here, this guy is going to get pushed up. So that methyl will be wedged. The other methyl may be hard to see until you draw on, say, the implied hydrogen. The implied hydrogen gets pushed up, just like the original methyl, which means that second methyl gets pushed down. I meant to have that. Okay. What happens with the rest of my structure? Okay, well, the carbonyls should go endo, which means they should stack underneath, and so I should see those as dashes. Now what I would do personally is clean up the drawing a little bit, turn those into solid lines. I use those again as my focal point to understand where the attack was coming from to come up with the geometry. Make sure I drop in my double bond, and I now have the product of this. Why do we get a screwball with this question? The answers were drawn with this structure in chairs. Okay? I could attempt to go through and redraw this into a chair. I would actually step away from that and focus more on the relative positions. I have my methyls aimed which directions?
Up and down.
Up and down is fair. Up and down is better. I actually like that. I was going to say trans, but our up and down makes more sense. So now I can go back to my chairs and I can be like, where are my methyls? Up and down in A. Where are they in B?
Also.
Also up and down. That one's a little bit harder because they're equatorial versus axial. Okay. The other thing I'd want to do is make sure that they come into alignment, the proper alignment with my pi bond. Pi bond isn't shifting somewhere else around the ring. So if I looked at my carbon, 2, 3, 4, so carbon 1, 2, there's the double bond, 3, 4. Carbon 1, 2, 3, 4, the double bond's in the right spot relative to those methyls. Make sense? The next part would be then dealing with the carbonyls. Okay, well, the carbonyls are located where?
Equatorial versus axial. I always.
Okay, and we'll still have issues with equatorial and axial. Okay, but this is down. I would say down. Technically, I should say down and down. So I would go back to my answer choices for A. Where is that one aimed relative to the ring? Down. Where's this one aimed relative to the ring? Also down. Okay, dealing with that equatorial again can be a problem. So what's the cheat? Draw the other atom. Where's the hydrogen aimed?
Up.
Very clearly up, which means the carbonyl must be aimed down. Right? Go to the other one. We have down and down. Okay? I would again try and make sure that we didn't get a weird shuffle on those. Okay? B, I think it has it a little bit cleaner, so we could even color in the new bond. There's our 4. Okay, so that makes sense with where they're located. If we look at A, a little bit harder to see because it's wrapped kind of around the structure. But we should see the purple new bonds in there, and that positioning makes sense as well.
So then they're both correct?
These would both be correct. Okay. Per whoever actually went through and did this one on the practice exam, what they went through and noted was that these were just chair flips of each other. Does everybody see that they're chair flips of each other? If you're making the face, that's fine. You just don't see that. Don't worry about it. Okay? Find a different methodology to process it. Okay? I, quite frankly, saw chair flips and went, bullshit. And I went through and did this. Then I went back and looked at the answers. I'm like, no, you're right. You win. Okay.
Who did that? Who did it? Identify
I'm going to
yourself.
guess Ivan, but I don't know.
Oh, yeah, I literally did the entire practice exam class, so it was like Irvin's.
Yeah, that's fine. So then there you go. And yeah, that's a phenomenal observation. Okay, and this comes to one of the reasons why I would push you to talk to other people. Okay? Just because I see something doesn't mean you're going to see it. Just because you see something doesn't mean I'm going to see it. Theoretically, I will be able to see it eventually because I've had a little bit more practice than you've had. Okay? But I may not even be able to pick it up. Okay? That becomes one of the things that is both incredibly fun and incredibly dangerous and painful about OCHEM. It all comes down to that viewpoint. And if you can't recognize that three-dimensional space, it's really, really challenging to manipulate. Some people just click, and there it is. Okay? And it may even be it just clicks in that one scenario, but in no others. That can still happen. Okay? So don't get frustrated with yourself. It's still a question of just trying to continue to manipulate those systems and get used to seeing those structures. For the record, that meant the answer here was A and B,
I mean, see.
which is C. Okay? We are at time, so I'm going to go ahead and stop. Oh, yeah, because